Hi everybody, this paper presents a model of a novel two-terminal floating gate transistor that operates in a low-power memristive mode for a computer-aided design framework of neuromorphic computing. It is done in collaboration with TowerJS. Neuromorphic computing is an emerging engineering discipline founded by Carver Mead that strives to produce the brain's cognitive and adaptive abilities in hardware by mimicking its architectural and dynamical properties to rethink the way computing is performed. Thus, several neuro-inspired architectures have been proposed, shifting the spotlight from the traditional von Neumann paradigm to neuromorphic computing to accelerate artificial neural networks computation in the analog level. Most of the neuromorphic computing research focus was on non-volatile memory devices that enable this paradigm. The concept of using non-volatile memory devices with adjustable conductance in analog neuromorphic networks to mimic the biological synapse is at least 30 years ago proposed by Carver Mead colleagues. They mostly used floating gate synapse transistors due to their compatibility with CMOS process as shown in the cross-sectional schematic and the corresponding layout. It is based on a MOS transistor with a double poly for control and floating gates implementation. This device operates in the subthreshold mode with the following exponential IV relationship, where the currents are below 1 microampere, represented by a multiplication of two dimensionless functions and resembles the synapse functionality abstracted by a multiplication of the weights and the input. The threshold voltage, which is a function of the charge amount in the floating gate, could be continuously modulated by applying high voltages to inject channel hot electrons or holes to and from the oxide. However, these devices had relatively large areas in all technology nodes that led to long time delays and high power consumption, in addition to their low endurance. In the last decade, the field of nanoelectronic memory devices has been revived by new developments. Two-terminal memristive technologies are of particular interest, including various technologies such as resistive RAM, STT-MRAM, and phase-change memory. These passive devices have small footprint, new computational capabilities, and diverse applications. They are considered promising as candidates to implement artificial synapses in the future. They implement the vector matrix multiplication, which is considered as the computational bottleneck of artificial neural networks in the physical level using Ohm's and Kirchhoff's laws. However, these devices are still immature for the very large scale integration necessary to obtain commercial value from neuromorphic computing, due to the variability and reliability issues and the lack of standard computer-aided design tools that enable very large-scale integrated circuits. Fortunately, in recent years, the non-volatile floating gate memory cells have been optimized, scaled down, and embedded in CMOS integrated circuits. A prototype of a three-layer mixed-signal neuromorphic network was implemented by a pioneering group in Memristive technologies using digital input analog weight arrays of floating gate cells redesigned from a commercial 180 nanometer NOR flash memory. The main advantage is the mature fabrication technology. The memory arrays have been redesigned to allow for individual, precise adjustment of the memory state of each device. Furthermore, two startup companies are using these technologies to accelerate artificial intelligence. Recently, in a paper published in Nature Electronics, we proposed a two-terminal floating gate memristive device called the Y-Flash, using a standard CMOS process. We emphasized on bridging the gap between the emerging computational capabilities of memristive devices and the technological maturity of floating gate transistors in a behind-the-paper post. Here, we present a neuromorphic-oriented computer-aided design framework of the floating gate memristive device. We reported on a low-power two-terminal floating gate transistor fabricated using standard single-poly technology in a commercial 180 nanometer CMOS process. Our device, which is integrated with an asymmetric readout transistor, can operate in a low-power subthreshold memristive mode, analogously to the floating gate synapse transistor, with a 3 orders of magnitude resistance dynamic range. Our device can be precisely tuned using optimized switching voltages and times, and can achieve 65 distinct resistive levels and 10-year analog data retention. Moreover, we experimentally demonstrate the feasibility of a selector-free integrated memristive array in basic neuromorphic applications, including vector matrix multiplication, spike time-dependent plasticity, associative memory, and a classification training. A news and views paper published in Nature Electronics highlights the importance of our approach and its potential in energizing neuromorphic computing. To commercialize very large-scale integrated neuromorphic systems, we need a computer-aided design framework compatible with the standard design tools that engineers from industry familiar with. Since the proposed device is fabricated using standard CMOS process and it resembles NMOS transistors, it is relatively simple to develop such a framework. We will go over the framework step by step in the following slides. The read mode of the Y-flash memristive device is modeled by the subthreshold current of the Y-flash device when the source's terminals are shorted and is described by a multiplication of two separable and dimensionless factors, where the first factor is a function of the applied voltage across the device, for example, 2 volt for read, and the other factor is a function of the threshold voltage, which is used as the state variable of the memristive device. This expression emulates Ohm's law with exponential IV relationship, similarly to the floating gate synapse transistor, but with VDS instead of VGS. In this graph, we can observe the shift of the Y-flash IV curves in response to programming voltage, which spans 1 volt state variable dynamic range and 3 orders of magnitude current dynamic range. While in the second graph, we can observe the currents of both transistors in the subthreshold mode and conclude that the total current is dominated by the read transistor, which helps us in modeling the read mode of the device. The nonlinear IV relationship is linearized for small signal changes to adhere to Ohm's law, where the device dynamic or incremental conductance is defined as the derivative of the current by the voltage around the operating point, which is the read voltage and equals to 2 volt. Small signal analysis is illustrated around 2 volt operating point. In this region, the IV is linear, and the corresponding resistance range is shown in the inset. We demonstrated the programming kinetics, which imitates the reset process of memristive devices. We applied 4.5 volt and 5 volt respectively on the drain pulses with 10 microsecond time duration, while the sources are grounded as shown in the cross-sectional schematic of the Y-flash device. We modeled and fitted the obtained measurements by the Lucky electron model of channel hot electron injection process of a standard floating gate transistor. All the model parameters refer to technology-dependent physical dimensions of the transistor and are specified in the paper. The state variable derivative is a function of the present state of the state variable and applied voltage, which adheres to the memristive kinetics definition. This procedure obtained a high number of resistive levels corresponding to the state variable updates, as shown in the inset, that are easily and continuously reproduced. Analogously, we demonstrated a Roizin process that imitates the set operation on memristive devices. We used 8 volt and 10 microsecond pulses applied on the source terminal as shown in the cross-sectional schematic of the Y-flash device. We modeled and fitted the obtained measurements by the vertical gate-induced drain leakage and band-to-band tunneling model of the standard floating gate transistor. All the model parameters refer to technology-dependent physical dimensions of the transistor are specified in the paper. Again, the state variable derivative is a function of the present state of the state variable and the applied voltage, which adheres to the Memristive kinetics definition. This procedure also obtained a high number of resistive levels corresponding to the state variable updates, as shown in the inset, that are easily and continuously reproduced. Here we specify our modeling methodology. As mentioned, we fitted the experimental measurements to the analytical model equations using MATLAB curve fitting tools. We simulated annealing techniques. Since the model is dynamic and has continuous time kinetics, thus it could be easily implemented using a Verilog A SPICE representation. We developed a Verilog A model based on the fitted parameters and used it for circuit design and simulations of different applications, which reproduced the basic experiments with high fitting accuracy, above 98%, as shown in the reproduced hysteresis figure of the Y-flash device, which is a typical characteristic to Memristive devices. This model allows the designer to explore preliminary results based on the Y-flash-based circuit topologies with high flexibility using adaptive behavioral and empirical parameters determined by the designer using a graphic user interface. A link to the model code can be found in the paper. Rather than enforcing deterministic dynamics, several applications take advantage of the non-deterministic memory for native stochastic computing, where the required randomness is intrinsic to the device and fundamentally changes its operating principle. Due to the stochastic nature of the injection and tunneling processes of floating gate transistors, the state variable dynamic model is modified to capture the stochastic variations by adding a probabilistic density function of an electron injected or tunneled into the floating gate during a time interval following Poisson process and multiplied by the statistical spread of the state variable. We fitted the proposed model to the experimental measurements and characterized the statistical distribution of the state variable and currents in erasing and programming modes, respectively, as shown in the figure. This model is also incorporated in the Verilog A-based SPICE model, and stochastic dynamics can be flexibly simulated and evaluate the overall effect on the performance. Due to the flexibility of the proposed model, other non-ideal sources could be also incorporated and behaviorally captured by the model, such as endurance and data retention degradation, and accordingly evaluate their effects on the overall system and application performance. After developing the deterministic and stochastic Memristive model in Verilog A SPICE model and small signal analysis, the symbols and schematics are generated, as could be seen from the figures that describe different circuitry modes, including program, erase, and read connections respectively, to be simulated in SPICE. A small signal equivalent schematic for linear analysis of the Y-flash device, considering various capacitors, is developed as shown in the figure. The maximum frequency of the small signal input is limited by the coupling parasitic capacitor of the two transistors. We performed spectral analysis on the modeled circuit by biasing the Y-flash in subthreshold and applying a small signal within the dynamic range. The gate source voltage is determined by the voltage division on the capacitive impedances. The total gate source capacitor is relatively lower than the gate drain capacitor, which includes the coupling capacitance. Asymptotically, the gate is floating and shorted to the drain. Therefore, the small signal schematic can be simplified as a variable resistor. At higher frequencies, the Y-flash operation is dominated by the capacitors, transitioning it to behave as an amplifier with capacitive and resistive contribution, rather than a pure resistor, which leads to a pole that degrades the gain function by 3 dB. Spectral analysis, as illustrated in the last figure, gives a maximum operating frequency range spanning 3 orders of magnitude corresponding to the state variable dynamic range. In parallel to the designed schematics, a layout of the device is designed using standard GDS masks and checked for design rules using the installed library's Process Design Kit (PDK) of Tower Jazz 180 nanometer power management technologies integrated in the Cadence environment. Then, a layout versus schematic (LVS) is performed to check if the given layout fits the proposed device, while it is represented using 2 NMOS transistors and a parasitic MOS capacitance. The same procedure is done to a 12 by 8 Y-flash based array. Then, RC extraction is performed to extract parasitic capacitances and resistors for both single device and the interconnect in the designed array. These steps were performed using Ashura. By applying these rules appropriately during the test, we validated the design correctness, meeting the manufacturing process requirements by launching accurate post-layout simulations. Cross-behavioral simulations could be launched based on those post-layout models and Monte Carlo simulation based on process variations, temperature distributions of standard NMOS supplied by the PDK. The noise characterization methodology for robust trainable circuits is not as stringent as for standard circuit design, where precise noise models of electric devices should be supplied based on a mass measurement. Here, non-ideal sources of PVT at CMOS peripheral circuits are calibrated and compensated for by configuring the analog non-volatile memory cells. This Y-flash device is employed to fabricate an array. The symmetric structure of the device is beneficial in mitigating reliability issues such as sneak paths, as shown in the figure, where sneak path currents pass over cells in opposite polarity and cancelled. In the same way for half select during programming. Our framework enables a reliability and signal integrity validation of such arrays after their physical design to be tested against such extreme cases and other disturbing effects, such as program disturb, which disturbs adjacent cells that share the same drain terminal and leak to the substrate via the injection transistors. The model allows the designer to incorporate the variation margin and hence qualitatively and quantitatively analyze its effect on the overall performance. Following to RC extraction, crosstalks, and IR drops can be evaluated and check their implications on the design constraints. To conclude this talk, we saw that floating gate synapse transistors are being reconsidered due to their technological maturity, while Memristive technologies are immature for commercialization and promising for the future. Aiming to bridge the gap between the technological maturity of the floating gate transistors and the computational efficiency of Memristive devices, we proposed a 2-terminal floating gate Memristive device in a standard commercial CMOS process and show promising properties for neuromorphic computing. We modeled the deterministic and stochastic kinetics of the device in Verilog A SPICE, generated circuits, and small signal schematics, designed layout that was checked using DRC, LVS, and RC extraction, and launched physical and behavioral simulations for signal integrity. This enabling by that a computer-aided design framework for developing very large-scale integrated neuromorphic systems for artificial intelligence in the future. Our ongoing research investigates neuromorphic data converters using floating gate memristive devices, which are considered as the computational bottleneck of analog neuromorphic computing. You are invited to my talk in this regard that will be given in Computing in Memory Date workshop. Thank you for your attention.